Hey, my name is Hanung Desta, and here I'll be presenting the Constant Velocity Lab for Physics 1. So, the purpose of this experiment is to observe the motion of an object that is moving at a constant velocity in one direction over a period of time and compare it to that of a computational model. The assumptions present are that the surroundings are completely frictionless and contain no air resistance. This is important to have because in the real world, these forces would prevent constant velocity from occurring without a constant external force being applied. Additionally, only motion in the x direction will be observed as said in the lab instructions. So, the y and z direction will be said to have zero motion. This graph shows a preview of the outcome of this experiment, where the motion of the object I rolled and the computational model are similar, but definitely not the same. The first fundamental principle that is vital for this experiment is Newton's first law, which states that an object in motion will stay in motion unless acted upon by an unbalanced force. So if an object has an initial velocity, it will maintain that speed indefinitely until a force is applied on it. Newton's second law is also important in this experiment and states that the net force is equal to the derivative of momentum over time, which is another way of saying it is equal to mass times acceleration. This is related to this experiment because we want constant velocity, which implies zero acceleration. And if there is zero acceleration, according to this formula, then that force is zero. Knowing this will be a big help when creating the computational model. Other relevant formulas include the velocity update formula, which says final velocity is equal to the initial velocity plus acceleration times change in time. The average velocity formula, which for constant forces is final position minus initial position over change in time. And the position update formula, which is just a rearranged version of the average velocity formula. So, in this experiment, my system was a golf ball and the surroundings a wooden table. The initial position of the ball was 0.0266 meters, the velocity was 0.378 meters per second, and the time was 0.0667 seconds. As you can see in this video, I applied a one-time force on the golf ball to roll it across the table, along with the tape measure, which is used to calibrate the tracker. There were 30 frames recorded per second for the tracker, and a point was plotted for every one over the span of 1.4 seconds and distance of 0.5311 meters. The initial position and time for the computational model created in GlowScript were set to be the position and time seen in the experiment, which were 0.0266 meters and 0.0667 seconds respectively. The initial velocity was set to be the average velocity of the experiment, which is 0.378 meters per second and calculated using the formula shown previously. The calculation loop had the net force equal to zero because no force was being applied on the ball after the initial push. At the velocity constant and the distance increasing by the velocity for every frame, or 0.0333 seconds. Here, you can see the graph that compares the positions of the tracker with the computational model. The two lines are very similar in that they are upward sloping and reach the same distance, but the computational model is much more linear and consistent than the observed, which is more curved. This is because, in the real world, forces such as friction and air resistance are present, which apply an acceleration on the ball, causing it to change velocity over time. The computational model does not have these constraints, and will instead have constant velocity the entire time. Potential errors in this lab include human and computational. For human, there is a chance that I rolled the ball with a force that caused an inconsistent velocity instead of a constant one. For computational, I might have inputted the wrong data points into the tracker or incorrectly created the computational model while coding in GlowScript. In the original experiment, moving to the right was considered to be the positive x direction, and the left was the negative x direction. There was also a positive velocity and slope for the graph. If I were to swap the axes, however, moving to the left would be the positive x direction, and the right would be the negative x direction. There would also be a negative velocity and slope for the graph. It might be possible for me to determine how many pushes and pulls are needed to have net force equal to zero, but it would be extremely difficult, as I would need to be aware of all aspects of the friction and be able to consistently apply the exact same force, which is close to impossible. So, in this lab, I observed the motion of a rolling object and compared it to a computational model, and also utilized Newton's first and second laws for calculations. Overall, the motion of the experiment and computational model are similar but not identical. Uncontrollable forces like friction and drag are always present and prevent constant velocity from occurring if an external force is also not contributing. Thank you.